Here's an example of how to use the ratio test to find the interval of convergence for a power series. That looks kind of nasty, but things can often clean up pretty nicely when you're using the ratio test. So remember how the ratio test works. The recipe for the series is known as generically the term a sub n. The ratio test says I need to know what happens to the relative size of consecutive terms as we go down the line. In other words, if I build the quotient a sub n plus 1 over a sub n, I'm looking at term 6 compared to term 5, or term 100 compared to term 99, or term 1001 compared to term 1000. And I need to ensure that that ratio stays less than 1 as n goes to infinity for convergence. If n goes to infinity, i.e. you're looking farther and farther out into the series and you're seeing this ratio be bigger than 1, that means that the terms are actually growing in the long run, and so there's no way you can do a summation of them and get convergence. So that ratio has to become less than 1 in the limit as n goes to infinity. And so we're going to construct this ratio and ask, what does it take for that ratio to stay less than 1? What values of x will make that ratio stay less than 1? So if a sub n is the general term, then a sub n plus 1 over a sub n can be written like this. I'm just going to build a sub 1 first. X minus 2, well, now to the n plus 1, divided by, well, what normally would be n is now going to become n plus 1, and since there's n, which is now n plus 1, plus another 1, that term will become n plus 2, and then when n is replaced by n plus 1, we get this. And then I'm supposed to divide that by a sub n, but we're working with quotients. Division by a quotient is the same thing as multiplying by the reciprocal, and so when I divide by a sub n, I'm just going to flip that around to multiplying by the reciprocal of the generic series term representation. And I'm going to put my absolute values around that, and I'm going to simplify that mess. Well, we got some canceling going on there. We got some canceling going on there. And then we have n plus 1 over n plus 2. So let's clean this up. The n plus 2 is still sitting around. Sorry, the x minus 2 is still sitting around. There's a division by 3 that survived the cancellation. And then we have n plus 1 over n plus 2. Like that. And now I'm going to look at this part of it. I've built the ratio of a sub n plus 1 over a sub n. Now I'm going to let n go to infinity. So the limit as n goes to infinity of a sub n plus 1 over a sub n is equal to the limit as n goes to infinity of this. Okay, now I'm not going to write that down verbatim because the first thing I'm going to do is recognize that this front matter here, this has nothing to do with n, and so it can be factored out of that limit. Like so. So I could have written the limit of this whole thing, but then the first step after that is to factor out all the stuff that doesn't have to do with n. So I've just gone ahead and done that. And remember, there are absolute values, and so they have to tag along when you're doing things like factoring. This limit is just 1. And so the limit of the ratio of successive terms as n goes to infinity looks like x minus 2 over 3. Absolute value x minus 2 over 3. For convergence, abbreviated, we need this x minus 2 over 3 to be less than 1. which means we need x minus 2 to be less than 3, which means we need x minus 2 itself to be in between 3 and negative 3, which means adding 2 across the board, we need x to be between negative 1 and 5. So this would tell us that as long as our value of x lies in between negative 1 and 5, this ratio will be less than 1, which means that this series will converge. And so this makes up the bulk of our interval of convergence. Now, here's the tricky part. It's not the tricky part, it's a footnote or a seemingly trivial detail that's actually quite a big deal. The ratio test itself says, hey, build this ratio. Take the limit as n goes to infinity. If that limit is greater than 1, then your series is not going to converge. If the limit of this is less than 1, then your series is going to converge. And if the limit of this as n goes to infinity is equal to 1, then we don't know. The ratio test doesn't tell us whether it converges or not. Now, this is the range of numbers for which that ratio would be less than 1, but it so happens that at the endpoints of negative 1 and 5, the ratio is equal to 1, right? If we went back to this and asked for where is the absolute value of x minus 2 equal to 3, we would have come back with negative 1 equals x and 5 equals x. So what we have to do is test the endpoints. And to do that, I'm going to flip to the next page because I'm kind of out of room. Remember that in the ratio test, we asked for when a ratio was less than 1 to learn when the series would converge. The test also tells us that if our particular ratio we worked with was bigger than 1, we would not get convergence. The ratio test tells us nothing when the ratio we looked at is equal to 1. The endpoints of this interval are where that ratio is equal to 1. So we still have to decide what happens at negative 1 and 5 specifically. And we do that by just trying them out. When x is negative 1, this series looks like this. Up here wants to be x minus 2, but specifically when x is negative 1, negative 1 minus 2 is negative 3. And negative 3 to the n is negative 1 to the n times 3 to the n. And then there's some denominator stuff waiting around like that. And oh look, cancellation. And the resulting series looks like this. You should recognize this one as a convergent series. It's an alternating series in which the terms get smaller and smaller as n gets bigger, and whose limit of the terms themselves, as you go farther out in the series, gets to 0. The alternating harmonic series is what this guy is, and he converges. And so that means that not only is the interval between x equals negative 1 and x equals 5 the interval of convergence, but we get convergence at negative 1 as well, which means when it's all said and done, we're going to have to write an equality there. But we're not quite done. We have to check the other endpoint. What happens when x equals 5? I've written down the whole series again, except for the piece with x. Let's take a look. Up here, the formula wants x minus 2. So specifically, when we plug in x equals 5, that becomes 3 to the n. Whoops. The n was already there. 3 to the n divided by 3 to the n. Cancel, cancel. And you should recognize that as a form of the harmonic series which diverges. And so what that means is that the overall interval of convergence is everything between -1 and 5, including -1, but not including 5. So we could write it in interval notation like that, or if you like the less than or equal kind of business, you could write it like this. All right, so recap. When you're looking for an interval of convergence and you're using the ratio test, you build the ratio test ratio, shake it out, and find out what it takes for the limit of that ratio as n goes to infinity to stay less than 1. That gives you the body of your interval of convergence, the interior, but then you have to test the endpoints individually to find out if you get convergence at either endpoint, and then include or don't include those endpoints as needed.